three variable systems. Three variable systems of equations. And we're going to do equations. We don't do three variable systems of inequalities, but just of equations. And what these systems are, the equations of them are not just straight lines. Some of them would be straight lines, just a line. Most of the equations represent a plane, like a flat plane. And a good example of a solution and what a graphical solution of a three variable system of equations would be if we took this front wall as one of our equations. That equation, if you were to graph it in a three-dimensional graphing system, it would look like this front wall, be flat plane. And then the second equation might be this wall over here, just a big flat plane. All right. And then the third equation could be the ceiling. Okay. And with three variable systems, when you've got three flat planes coming together, where does this wall, that wall, and the ceiling meet? Right up there in that corner, right there. That's one point. That's what it looks like when there's exactly one solution for a three variable system of equations. Remember, with any system of equations, no matter what size, we did two variable last week, we're doing three variable right now. No, if we had 14 variables, there are only three scenarios that can happen. One of the scenarios is that you have one solution. Remember, that was consistent and independent. Those words. So if we had three variable system and there was one solution, graphically it's going to look like that corner right up there at the top, just that one small point. Another situation would be if there were no solutions. We had that with two variable systems. That same thing could be the case for three variable systems. Using the idea of the walls as being equations, what would be an example of a three variable system that has no solutions? Think about what the graph of lines looked like and what we called them when there was no solution. What would the graph of planes look like when there's no solution? Three parallel planes, that could be definitely a case. If we think about the room, the floor and the ceiling, they're parallel to one another, right? They never touch each other, right? And then, I don't know if you know this, but above this ceiling here, there's another ceiling, that's the roof, right? So three parallel planes would be like the floor, this drop ceiling that's in here, and the roof. They're all parallel. They never touch each other at all. That's one example of an inconsistent system with no solutions. What would be another example? That's a very good example. Not the one I was even thinking. What if the back wall and the front wall were two of our equations and the ceiling was the third one? Is there a place that the back wall, the front wall, and the ceiling, all three come together? No. The back wall meets the ceiling. The front wall meets the ceiling. But nowhere do all three of them come together. So there's another example of a no solution system out of that. So there's definitely some things that can happen there. Now, when we're talking about a three variable system, there are multiple ways. Well, there's representations of this, of infinitely many solutions. Remember, that was consistent and dependent. When you got three variable systems, 3D graph is planes, like flat surfaces. Where do three flat surfaces come together? Somebody come up with an example of that. I'll try to find it. Think about this. Got a book. any book, notebook. Here's a flat plane, this brown cardboard one, right? Okay. Pick up this piece of paper. That's another plane, right? Okay, so right now these two meet at one spot, the spiral bound part of the notebook, correct? Okay, if I pick up a third plane, so I've got that one laying flat, this one up here, and I pick up another piece of paper, that's three planes, right? They're all three meeting where? At the spiral. That creates a line, doesn't it? And a line has how many ordered, and in this case, ordered triples? How many are on a line? We can't count them all. There's once I count this one, I can go to the next one and the next one and the next one. So an infinitely many situation is where three planes come together and they all intersect at a line out of that. That's what it looks like graphically out of that. So sometimes a picture in your mind of what's happening can kind of help you make some sense of this stuff. So let's look at a three variable system, and we just want to start off with something pretty easy. Is -1, +1, -5 a solution to, and then here's a three variable system, -2x plus 4y plus 4z equals -14, 2x minus 4y minus 3z equals +9, and then -2x plus 2y plus 3z equals -11. So they give us this three variable system of equations, and they're asking, is this ordered triple? And the way that the ordered triples are written are in alphabetical order. So if the letters ever change from X, Y, and Z, and they're another set of letters, it's always alphabetical order. And so if it's A, B, and C, it's A is the first letter, B is the second, C is the third. If it's R, S, T, it's R, then S, then T, as far as the ordered triple goes. So how do we verify whether or not that ordered triple is a solution to that system? Plug them in. It has to work in how many? All three to be a solution to this system. So we're just going to check it by saying -2 times -1 plus 4 times 1 plus 4 times -5. We're going to see if that equals -14. So that would be 2 plus 4 is 6 plus -20. 6 plus -20 is -14. It checks in the first one. Go to the second one. 2 times -1. Oops, it's a -4 times +1. And -3 times -5. And we want to see, does that equal +9 like the original problem does? So that's -2 minus 4 would be -6 plus 15. -6 plus 15 is 9. Checks in the second one. So far, so good. We got to check it one more to verify that it works. -2 times -1 is 2, plus 2 is 4, plus -15. -15 plus 4 would be -11. It checks in all three. So we can say yes, -1, 1, -5 is the solution. Or let's say a solution. We don't want to say it's the solution because we don't know if that's the only one. Unless we solve that system. All right. Example B, let's actually get into solving a system and kind of go through the process of this. Kind of, I'll preface this in the fact that when you're solving a system of three variables, your way may work Somebody else may do it a different way, and it still get the same answers and the correct answers. Okay, you don't have to do it the same way every time. And there's really not a set thing that says, hey, you have to eliminate X first, or you have to get rid of Y first, or you have to get rid of Z first. It doesn't matter. As long as you're taking and getting rid of variables and following the process kind of in the right way. Okay, so let's get a system here. Let's say 2x plus 3y minus 4z equals -9. Negative 2x plus y plus 4z equals 5. And then the third equation, it only has two variables in it, which most of the time makes it a little easier to do. So we're starting out with something kind of easy. I'm going to take you through how I like to do these in a way that I think makes this more accessible to everybody, because it's organization is the key. If you just go all willy-nilly and trying to do this, you can get lost in it real quick. And it's very difficult to go back through any of your work, even for you to do it yourself, to go back through what you did if you don't have kind of a system that you're using, okay? So I'm going to show you the system that I use. Is this the only way to do this? No, but it is, I think, a good way to do that. So what I do is I number the problems. This is number 1, this is number 2, and this is number 3. Really innovative way of doing things, right? Numbering things. That's but it helps me decide what I'm going to do. Okay, so what I'm looking at here is I see a 3-variable system in which 2 of the equations have all 3 variables, and this third one only has 1 of the variables. Okay, what do I notice about these 2 that have 3 variables? I got opposites on what? On the x's, and happen to be opposites on the z's as well. If I put those 2 together first, what's going to happen? So I'm gonna look at that. I'm going to put 1 and 2 together first, and I'm going to eliminate x. Maybe that's what my goal is. The reason I would try to eliminate x on that one is because this third equation doesn't even have an x in it. So if I can get an equation that doesn't have x in it, I can use it with this one to help me get my other variables. Okay, so I'm going to eliminate x with those 2 equations. So I'd have 2x plus 3y minus 4z equals -9, and then -2x plus y plus 4z is equal to 5. Bless you. Bless you again. If I add those 2 equations together, the x's do eliminate one another because they're opposites, just like you guys said. 3y plus 1y is 4y, and it just so happens that -4z and +4z go together and eliminate as well. That won't always happen. It just happens to work on this one. And then I get -9 plus 5, which is -4. I lucked out, and I got an equation that only has 1 variable left. That won't always happen. It works out nice for this one. But I can simplify this equation and get y by itself, right? By doing what? Divide by 4. Oh, if I do that, I get y is equal to -1. I've already got one of my answers. Does that mean I'll get the other 2? No, it just means I have one of the answers. Okay, I've got to get x and z out of that. Well, because I have y, I can take that and go somewhere and try to get one of the other letters. So I look for an equation that doesn't have all 3 letters in it. I happen to have one of the originals that doesn't have all 3. So I'm going to substitute the -1 into this equation for y. And that will give me an equation that only has z in it. And I can solve that. So I'm taking -1, replacing y. It'd be -1 minus 4z is equal to 1. So that's 1 minus 4z is equal to 1. Subtract 1. And I get -4z is equal to 0. What does that mean? that z is going to be equal to 0. That's exactly right. Because I divide by -4, 0 divided by anything is 0. I got 2 out of 3. That ain't bad, but it ain't done. Okay? So I'm going to take z is equal to 0 and y is equal to -1, and I'm going to plug those back in where? To one of those other equations that has all 3 variables in it so that I can find x. Because I need an equation that's got an x in it, right? So I'm going to plug those in. So 2x, I'm just going to the top one, plus 3 times -1 minus 4 times 0 equals -9. So I just went to the top one there. All right? 2x minus 3, 4 times 0 cancels out. Got -9 there. That's not too bad of a one to solve. Just got to add 3. That's going to be -6 is equal to 2x. So what's x? -3. Now I have all 3 variables. I have the solution. This is a one solution system because I found all 3 variables. That solution is an ordered triple, -3, -1, 0. That's how you write the answer to a 3 variable system. X, then Y, then Z, or whatever alphabetical order for your letters, or if they change the letters. On the practice you got today, they changed the letters up. Just use different letters. It doesn't matter, though, as long as it's alphabetical order. Okay? Let's look at another one. -6x plus y plus z is equal to 21. -6x minus 2y plus 5z is equal to 23. And then -4x plus y plus 2z is equal to 12. And I'm just going to go ahead and number those equations, 1, 2, and 3. All right. Now, this one, we don't get the shortcuts on because all 3 equations have all 3 variables. So this one is a full-blown 3-variable system that there aren't really many shortcuts to. Okay? So what we want to do here is we want to just look at these 3 equations and look to see if there's something that would easily eliminate if I paired a couple of them together. Okay? Well, if I look at 1 and 2, I've got -6x on both of them. I've got 1y and -2y, so that's not too hard to change up. And I've also got 1z and 5z. Those aren't really hard to change up. You know, get rid of something there. But I think the easiest thing for me to do would be to take the first 2 together and get rid of x, right? Because I don't have to change it very much to get rid of x. What do I have to do to one of those equations to get rid of x? Multiply it by -1. So I'm taking number 1 and number 2 together, and I make a note here that I'm eliminating x. So I help myself if something goes wrong. If I've got a note about what I did right there, that's going to help me go backwards and try to find my mistake if something went wrong. Okay, so I'm going to multiply the top one by -1, so that when I add these together, I'll have 23 and -21. So I'll get a positive answer out of that. Not that it necessarily matters, but that's what I'm going to do. I'm going to multiply the top one by -1 and get 6x minus y minus z equals -21. And then I have -6x minus 2y plus 5z equals positive 23. When I put those 2 together, the x's eliminate one another, just like we planned. -1y, -2y is -3y. -z and positive 5z would be positive 4z. And then that would be positive 2. So I'm going to hang on to that equation. I'm just going to put a box around it so that I know I can get back to it pretty quickly. Okay? Notice that we've still got two variables in there, so we can't just solve this and get an answer. We've got to do something else. What we've got to do with three variable systems is you've got to pick another pair and eliminate the same variable. Okay, so we can't use 1 and 2 together again, but I can use 1 and 3 or 2 and 3 to get rid of x. I still got to eliminate x because I need another equation that has these same variables in it. Okay, so which pair do you want to use? 1 and 3 or 2 and 3? 1 and 3 looks fine to me. It really doesn't matter. It's about the same either way. So if we put 1 and 3 together, 1 and 3, and we're again going to eliminate the same variable, x. When you're doing a three variable system, the first two steps, you've got to eliminate the same variable. If everybody has all three variables, you've got to eliminate the same variable twice. Okay? So we're taking 1 and 3 and doing that. So I'm just going to copy down 1 and 3 again here. Negative 6x plus y plus z equals 21. And then we'll do the work here. So negative 4x plus y plus 2z equals 12. What do I need to turn those x's into in order to eliminate them? I can turn them into 12s. One needs to be a positive 12, one needs to be a negative 12. Okay? Because 12 is the least common multiple between 6 and 4. That's why we're going for 12. So you choose which one you want to make positive and negative. I'm going to make the bottom one turn into a positive 12 and let the top one stay the negative. Okay? So I need to multiply the top by 2 and the bottom by negative 3. By multiplying the top by 2, it changes my problem into negative 12x plus 2y plus 2z equals 42 now. And then the bottom one, negative 3 times all of that, gets me a positive 12x. That's what I needed. A negative 3y and a negative 6z. Negative 3 times 12 is negative 36. So now I have opposites on the x's. You could have gotten opposites on the x's by just saying, okay, negative 2 on the top one and positive 3 on the bottom. It does the same thing. Okay? Again, there's just a lot of ways you can do this, but I'm trying to show you an organized method of doing that. Now, when I put these two together by addition, the x's eliminate one another. That's what we tried to do. The y's, negative 3 and positive 2 together would be negative 1y. Positive 2 and negative 6 would be negative 4z. 42 minus 36 is positive 6. Now I have these two equations that are in the boxes. What letters do they have in them? Y and z, the same two letters. Okay, that's what we need. We have a system that we can work with two variables in it. So this goes back to what we did last week. So we're going to take these two and put them together. Well, the good thing is the way it happened to work out, not that we tried to do it this way. Look at the z's. Negative 4z and positive 4z. Elimination would work really well with those, right? So that's where the elimination is a good thing. So I'm going to use elimination to work that system. Negative 3y plus 4z is equal to positive 2. And then we have negative y minus 4z is equal to positive 6. When I put those two together, I don't even have to do anything to them. The z's will cancel each other out. And I'd get negative 4y is equal to positive 8. Hey, now I got a one-stepper to do. That's an easy one right there. Divide by negative 4. And y is negative 2. I have a y value. Where can I go to get another variable's answer? Which ones?
The negative y minus one that has a y in it.
Yeah, one that has a y and one other variable. So we're going to use one of these two that we used in this system. So it's like we're taking this system and we're trying to solve it first. So if we plug -2 into one of those for y, we're going to get z. So I'm going to, if I put in -2 minus 4z equals 6. So that'd be 2 minus 4z, 6 minus 2, -4z equals 4. Z is equal to -1. I got 2 out of 3. How do I get the third one? Plug them in, go to find x. We'd have to go back to one of the originals. Any of the 3 originals that you want to use. It does not matter which. I don't usually think about this very long. I just usually go back to the top one. But you can use any of those you want to. By going back to the top one, I got -6 plus y, so that's -2, plus z, so that's the -1. And now I've got a pretty easy equation. -6x minus 3 equals 21. I would add 3. Get 6x is equal to 20. -6x is equal to 24. And then divide by -6. And x is -4. We have one solution, -4, -2, -1. Is this quick and easy and simple? No. It's not quick. It's not simple. But the math we're doing is not really hard. It's easier. It's pretty easy arithmetic. It's just a substitution and elimination like we did from last week. It's just you're having to do it a couple of times. 3 times, in fact, for this problem to get the answers. There were 3 variables. So it makes sense you'd have to do 3 different things to get there. For 2 variables, we had to do at least 2 different things to get the answers out of that. Let's look at another one and see what happens here. So the first example, or first equation is x minus y plus 2z is equal to 2. And then second equation, -5x minus 2y minus 5z is equal to 27. And then the third equation is 2x plus 5y minus z is equal to -3. Looking for things that would be easy to eliminate or maybe already have opposites. Doesn't look like we have that on any of these. So we really get to choose whatever variable we want to get rid of. I'm looking at either the x or the y because they, z would also be fairly easy to do because they all have a 1 in front of them in one of the equations there. So that makes it easy to do elimination with. Let's eliminate y's this time instead of x, just to change it up a little bit. So if I took number 1 and number 3 together first, and we eliminate y, what do I have to multiply the first one by to get it to eliminate y? 5, because I need this to be -5 right there, right? Because there's a +5 here. So I'm going to multiply the top one by 5 and get the bottom, so I can get the y's to cancel out. So that's going to give me 5x minus 5y plus 10z is equal to 10. And then the number 3, I'm not changing at all. I'm just going to get 2x plus 5y minus z is equal to -3. And then when I add those two together, the y's do go away. I get 7x plus 9z is equal to 7. Okay, so that's, I need to take a different pair and get rid of y's. So I did 1 and 3. Is it easy to change a 2 into a 5? No. Is it easy to change a -1 into a 2? That's a lot easier to do, right? You don't have to multiply both. So if we what do we multiply the top one by to get an opposite with number 2? If we multiply the top one by -2, we can eliminate y again. Again, remember your process is eliminate the same variable twice. Okay, so we're multiplying the top one by -2, so that's going to give me -2x plus 2y minus 4z is equal to -4. And then the second one, I'm just copying down. So when I add those two together.
Mr. Isbell?
Yes, ma'am.
I need to move you along to the office, please.
Is it urgent?
After the bill's gone.
Okay. All right. So we've got -2x, -5x is -7x. The y's cancel. There's -9z, and 27 and -4 would be 23, right? Now we have two equations that have the same two variables in them. This one and another one that's in a box. All right? Now, put those together as a system. What do we notice? We got x and z's both have opposites on that, right? So 7x plus 9z is equal to 7. And then we've got -7x minus 9z is equal to 23. When I put those two together, what happens? You get 0 equal to 30. Does 0 ever equal 30? No. So what does this mean? That there's no solution. If you did this same process and you ended up with 0 equals 0, what does that mean? Infinitely many solutions. So process is key here. Eliminate the same variable twice, or if you happen to have one equation that has a variable missing, go to eliminate the one that's missing in the other pair. And it can get you a shortcut out of that. All right. I'm gonna go ahead and give you